Hello, and welcome to episode 222 of the Hackaday podcast. I am managing editor Tom Nardi, and if you're a regular listener, then by now you'll have realized that something has gone terribly wrong. That's right, regular host Elliot Williams has taken some time off and left me in charge of recording this week's episode. Well, sort of. What he actually said was that we could just skip doing the episode this week since he's the one who edits it and puts it all together. Rather than take his sage advice, I have decided to cobble something together to the best of my abilities. To keep the editing burden low, I've jettisoned the live co-host and will instead utilize some pre-recorded segments. Specifically, we got a quick hack coming from Jenny List, which is nice since she's not somebody we often get to have live on the podcast. And then we have some interviews conducted at the Vintage Computer Festival East a couple months ago that were very interesting, but just ended up running a little bit too long to turn into a video as we did with the other ones. If this is all sounding very familiar, you might remember I did something similar for episode 173 around this time last year, and if we're all lucky, I won't have to do it again until 2024. Alright, so we usually start the episode off with some news. I haven't had much time to look up from the computer this week, with Elliot being away and everything that entails. But I can tell you that where I am, here in the northeastern United States, has resembled something of a hellscape for the last couple of days due to Canadian wildfire smoke coming down south and turning the skies orange. So that's been a lot of fun. It actually has got folks on the Hackaday Discord server talking about things like DIY air filters and the sort of particulate sensors that are available on the market, should you want to spin up your own air quality monitoring station. And, as we've seen with other previous wildfires, say in California, I'd be willing to bet that when the dust settles, both figuratively and literally, next week, that we'll start seeing people send in, various hacks along those lines that they put together during the worst of this. So, that's something to look forward to seeing when you come out of your survival shelter. In Hackaday news, the op-amp challenge has now officially come to a close. We'll take the next couple of days to go over the entries and get the judging done. Hopefully have results out for that pretty shortly. We do get the occasional complaint, I suppose you'd say, about how long it takes to judge the contests. And, I get it. If you've got an entry in the running, you're eager to see what the results are. But, there's a lot of legwork involved. This time around, we've got 80-something entries that we need to go through, and to do them justice just takes time. I do believe we've bumped up the number of judges, though, this time around, so we'll look to balance the workload a little bit better and hopefully get that out quicker. So, look for the winners of the op-amp challenge to be announced sometime this upcoming week, and right after that, we'll launch our next contest. I don't think I'm supposed to reveal the theme for it, but I'll give you a hint that it is a follow-up to what was one of our most popular contests in recent memory. So here's hoping that lightning strikes twice. And then finally, we're still in the Green Hacks Challenge of the 2023 Hackaday Prize, which will be running until the 4th of July. So still plenty of time to get your planet-saving hacks in.
This is a journey into sound.
What's that sound?
What's that sound?
So this week we had a particularly challenging sound. If you're a regular listener to the podcast, you'll probably know I seem to struggle with them regardless. But looking at the results, it seems like the listeners didn't fare too much better this time around. If I'm pulling the data correctly, because I've never done this before, we appear to have 43 entries. And of those, 9 correctly guessed that yes, it was a volcano. And a few of them even correctly picked out that it was an Icelandic volcano, which, only the listeners of the Hackaday podcast, right? We have some pretty interesting entries. Weather on Mars, that's a good one. I thought something along those lines. So we said the inside of air conditioner ducting. Sure, why not? Exhaust fan for the Chicago subway system is quite particular. Multiple jet or rocket engines, air blowing out of the cooling duct in a freezer, jet engine noise from inside an aircraft, that's a good one. Recorded from Baikonur when those guys took off to fix Salyut 7, that's a nice reference. Data center, I could see that one for sure. Several people said glaciers. which is a good guess. Specifically, glaciers cracking in half, I guess. Rocket launched to orbit, jet or rocket engine, hydrothermal vent. Yeah, actually, we have several people who said hydrothermal vent, which, I mean, yeah, but no, because it's underwater. I don't think we can fairly call that a right answer this time around, given what the sound was like. What's this? The sound of wind on Venus. Yeah, okay, it's another one. Some really good answers here. All right, so we have 9 people that said specifically a volcano, and I know that Elliot likes to come up with cute little ways of generating the random number that picks the winner. So I am going to ask this idiot Google Bard to write me a Python script that generates a number between 1 and 9, mainly because I like to see the ridiculous answers it comes up with. And this time, now that I'm recording live, it managed to spit something out sensible, so we shall still run it. And the number is 8. Actually, wait, let me run it again to make sure it's actually seated with a number or something here. Okay, yes, it was not 8 the second time. So who is 8? 8 is Albert, that said active volcano. Well done, Albert. Assuming you have not won already, because only Elliot would remember that, we will work on sending you a coveted Hackaday Podcast t-shirt that I should say not even I own.
Hi, it's Jenny List here with the quick hacks for the week of the 1st of June 2023. First up, there's a piece that went out last week. It's what makes wedge coils better than round for PCB motors. And the guy doing it is Atomic 14. And what he's done is he's done an investigation into the layout of planar coils for a planar motor to get the best distribution of magnetic field to get the best performance out of the motor. And what he's done is he's taken 4-layer printed circuit boards to make multi-layer coils in PCB, which is kind of a neat technique. And he's made 2 different motors, one with an array of 6 circular coils around a rotor, and another with an array of 6 hexagonal coils of roughly the same size. And he's measured the performance of them. And he finds that the hexagonal coils are a bit better than the circular ones, and tries to go into the detail of how it's done. I thought it was an interesting dive into some of the theory. We all know how a electromagnetic motor works. There's an interesting dive into some of the things behind the performance of the motor. So that was definitely worth a read. Next up, it's one that went out on the 8th. It's actually one I wrote. The title is Apple Invent the Mechanical Watch, which is a bit of a joke on the Apple fanboys. When Apple bring out a product, they all claim that Apple invented it, even when everybody else has been using it for ages before Apple produced it. But what this is a guy called Nano Robot Geek. And what he's done is he's taken an early model Apple Watch, which are now out of support, so they're basically e-waste. He's taken one of the slightly upmarket ones with a very fancy metal case, and he has fitted a generic Seiko mechanical watch movement into it. And it's not just that he's fitted a watch movement into it. I mean, most of us could probably gut an Apple Watch and fit a watch movement into it. It's the way he's done it. He's done an absolutely beautiful job. He has retained the original Apple crown wheel, which of course is off to one side. It's not in the center like most wristwatches is. Now, on the Apple Watch, it operates some kind of rotational sensor. But in this case, he's got to both transfer the rotation to the Seiko mechanism and also transfer the action of pulling it in and out. So he's made a lever linkage and a little pulley linkage at the same time. And the engineering is very tiny and very beautifully done. But that's not all. He's created a stunning zirconium front plate for it. So it actually looks like it might even have been an Apple product, though of course it isn't. But the main thing is he's taken a piece of e-waste and made something that will actually last for quite a long time, and it's actually rather beautiful. The third piece I want you to all have a look at went out on the 5th, and the title is Protect Vintage Gear with Easy Capacitor Reforming. Now, we're all used to old pieces of electronic equipment having problems with electrolytic capacitors that have died. Now, most of us have probably recapped something in the past, but what certainly I didn't realise, and probably many of you might not realise as well, is that electrolytic capacitors can actually be reformed. They work on an oxide layer on the plates inside, and the electric current while they're in use causes that oxide layer to stay in place and reform itself. But if they're not in use for a long time, then the oxide layer degrades, which can, of course, give them a significant DC resistance, which causes them to heat up and explode. What you can do is you can reform them. You can rebuild that oxide layer by applying a gentle current for a period of time, and you can bring an old capacitor back from the dead, which is certainly quite a fascinating thing to know. It's something I, for one, will probably try at some point. I won't necessarily try it with a piece of equipment that I really care about, but to find out whether it works, it's certainly an interesting experiment to try. So there you are. Those are my quick hacks for the week.
Quick hacks.
So again, special thanks are due to Jenny List for providing us with that quick hack segment on relatively short notice. Jenny is always on the move, and knowing her, that was probably recorded from her cabin aboard an overnight ferry or something equally European and romantic. Now to wrap things up, as promised, we've got a couple interviews here that were recorded live at the Vintage Computer Festival East in New Jersey a couple months back. Now I should say that for reasons that aren't particularly interesting, we only had a mic on the person being interviewed, so there was a little bit of technical wizardry involved in bringing up the audio for the questions, so you might notice there's a little bit of a disconnect there, but I promise you these questions were asked live. It wasn't pieced together from multiple recordings. It's just the relative amplification of the two tracks. So first up, we've got David Lovett, who runs the Usagi Electric YouTube channel. The discussion here is largely about his vacuum tube-based 555 timer, which he's been documenting on his YouTube channel for some time and had brought along with him to show off at VCF. If you haven't seen it already, it really is a gorgeous piece of hardware, and it was great to get a little more of the backstory about how it was built.
My name is David Lovett. I run the YouTube channel called Usagi Electric. I have to apologize, my voice is thrashed, as is understandable. It's very loud in there, and we're having a great time here at VCF. But yeah, I mostly work on old stuff. I started working on vacuum tubes and digital circuits, which is kind of a rare thing. Most people use them for audio. And then I transitioned into a little newer, like 1970s, 1980s TTL level stuff. And that's kind of where I hang out. I've got a vacuum tube computer that I'm building, but I'm kind of unhappy with the direction it's going, so it's going to get a rebuild. And I've got a Centurion mini computer that I have resurrected from the brink.
Wonderful. Can you tell me a little bit about the name Usagi Electric?
So Usagi is just Japanese for rabbit, and the short story is that I like rabbits. Do you want the long story?
Nah, it's probably good enough for now. I assume you have a video explaining all this.
I don't.
Oh dear. Okay.
No. We were in Japan. We were at an izakaya in Japan, and I was there with a buddy of mine, and we were drinking. And in Japan, you drink in bars. That's just what you do. But you have a sake bottle that is your bottle. It's your keep bottle, and they just refill it. They don't ever replace the bottle. And so you write stuff on it to make it your bottle. And we wrote Usagi Motors because I like rabbits and I liked cars. And then I just transitioned that into Usagi Electric.
Naturally, yeah. I had the sense of you were a Japanophile, definitely.
Well, I did live there for 7.5 years, so.
That would do it. So we were talking a moment ago, you've got this very interesting prototype where you've gone from large-scale integration to enormous-scale integration.
Yeah. So this is my all vacuum tube 555 timer. The only thing on here that you may not have been able to find in the 1940s would have been the little potentiometers that I used to tweak it. But potentiometers did exist in the 40s. They just would have been a little bit bigger. So you could have absolutely built this 80 years ago.
Tell us the significance of the 555.
So the 555 timer is probably the most ubiquitous IC ever made. The guy who created it, his name escapes me at the moment, but it's a beautiful mixture of analog and digital. So it has 2 comparators on it, and it has a 3 resistor voltage divider. One at 2/3 VCC, one at 1/3 VCC. And they trigger the 2 comparators depending on whether the threshold or the trigger pins have been hit. And those comparators feed into the set or reset pins of a flip-flop. And a flip-flop is an inherently digital device. So comparators are very much so analog and flip-flops are very much so digital. So this allows you to build like an analog RC circuit that triggers a flip-flop to give you a digital output. So you can take a capacitor and a resistor and have it charge up to a certain 2/3 VCC, triggers it, and it discharges down to 1/3 VCC. And it's got a little discharge transistor in there to allow that discharge to happen. And so then you have this nice sawtooth of the capacitor charging and discharging. But whenever it hits 2/3 and 1/3 VCC, it flips the flip-flop. And so on the output, you get a nice clean square wave. And so it was great for building clock circuits, watchdog timers, pretty much anything. It created kind of a meme of should have used a 555.
So you can build things that oscillate. Can you build other circuits out of it?
So the kind of the 4 main things that people use 555s for is astable multivibrator. So that's creating a square wave out of it essentially, and you can change the resistor and capacitor values to make it faster or shorter, and change the duty cycle on it, so you have different size on and off times. You can do a bistable multivibrator, so that you just hit it and it stays on, or you hit another pin and it stays off. Essentially, you're bypassing the comparator section of it and just using the SR flip-flop. You can do a monostable multivibrator. These are really interesting because you hit a button and then it pops on and stays on for a set amount of time, and then it turns off and stays off. So it's called monostable because it's stable in one state and it's chaotic in the other state. And the other state, in this case, is on. So you hit a button and it turns on for a set amount of time. That's based on your RC time constant. And then the final one that people use it for is Schmidt triggers. So if you have a signal that kind of is unstable between 1/3 and 2/3 VCC, it's not going to cause the output to change. The outputs has to be either above 2/3 VCC or below 1/3 VCC for the SR flip-flop to change state. So you can have a slightly unstable signal and it'll only change the output when it goes to either full high or full low. And so that's how you can turn an unstable signal into a very stable signal coming out of the other side. So Schmidt triggers are really great for it, but there's a lot of people that are a lot smarter and build more insane things.
So are there things that the 555 can't do?
No. I mean, I've seen it's
I've heard of somebody trying to build an entire computer just out of 555.
Yeah, so that's the thing. It's a flip-flop. So actually, building this out of vacuum tubes is quite interesting because the concept of a flip-flop was pretty much what IBM built everything around. So they called them triggers back in the IBM 604 days, 650 days. And it was just two triodes cross-coupled. That's exactly what this is. That's exactly what the SR flip-flop on the real 555 timer chip is. But if you have a flip-flop, if you have that trigger and you interconnect them in different ways, you can get complex behavior. So IBM built their entire computers based around this concept of triggers in different setups. So, well, that's what this is. This is a trigger that you can set up in different ways, which means you can get very complex behavior out of using just 555s. Is that the best way to do it? Absolutely not. Is it the craziest way to do it? Absolutely.
This one's a little bit larger than your usual 555. Right?
Yeah, so I like to call this the world's largest 555 timer. And I mean, that makes it sound like it's going to be massive, but I mean, it is still quite big.
Compared to your
regular 555, which is the size of your pinky there.
Yeah.
Because it's done out of vacuum tubes and because it's done at very low voltages, vacuum tubes generally like triple-digit voltages, minimum 100 volts, sometimes up to 300, 600.
Yeah, I've always been amazed at if you work on vacuum tubes, you have to be very careful to only use one hand and
Oh yeah, the hand
rest
in
of
the
that.
pocket rule, so you don't kill
Yeah,
yourself,
yeah,
stuff like
exactly.
that. I'm kind of dumb, and I like to stick my fingers in circuits. So if I had, 600 volts of potential on tap or 300 volts of potential on tap, that could end up poor. But it turns out that depending on the tube, some tubes work better in different voltage ranges. And through personal testing, I discovered that 686 is fantastic at very low voltages. So I'm using plus 24 and minus 12 volts here.
Oh, wow.
Now you do need a negative bias voltage. This is particularly useful for building inverting amplifiers because you want to pull the grid of a tube to a negative potential in relation to the cathode. So I have the cathodes all tied to ground on my amplifiers. So I need to get the grid negative in relation to that. So I got to pull it to a minus voltage. So I need that negative bias on there. But also the long-tailed pairs that make up the first stage of the op amps here, they also need a negative voltage. So it would be better if it was symmetrical, like plus 24, minus 24. But I used plus 24, minus 12 because that allows me to do some tricky things with the filaments.
So let's see. So you've got two op amps that are essentially functioning as comparators on the input,
That's correct.
and those are feeding into a flip-flop. Is that right, or do,
That's
do you have a gain stage in between there?
So we've got the two op amps make up the long-tailed pair, but the output coming out of that is minuscule, tiny. I can't really use it, so I have to amplify it. So I have one amplifying stage. That is not quite enough, so I send it into another amplifying stage. That is enough, but now the signal's inverse of what it needs to be. So I throw it into another inverter on the end so that I get the correct signal out the other side. That's why there's 5 tubes per op amp. And there's, like we said, 2 op amps. And the op amps are really just operating as comparators. And then we have the SR flip-flop here in the middle. So the outputs of each op amp go to the set or reset pins of the SR flip-flop. And then the output of that SR flip-flop is our output pin. That's what we get on the output on the outside. And I have that going through a cathode follower buffer.
For your SR latch in there, are you using more or less the same circuit that IBM used with their triggers and all the rest?
Pretty much identical to your standard SR latch flip-flop. I mean, I pretty much copied what was just the standard go out there. So the op amp design here with the gain stages is based almost entirely on the Philbrick K2W op amp, which was a vacuum tube op amp that Philbrick used to build analog computers and a lot of other really cool stuff. The SR flip-flop design is just your standard cross-coupled element. So you could build it with transistors, you can build it with tubes, it's pretty much identical. The cathode follower buffer is just a buffer for the output. That's pretty much like a emitter follower or whatever the transistor equivalent is. And then we just have a discharge tube that works exactly the same as the discharge transistor in the real version, 555.
Neat. I can't remember offhand. Do you remember how many transistors there are in a real 555?
Oh, no, I can't answer that one. I don't remember. It's small. I mean, it's not many.
Okay. And this is just a single pentode per case that you have this?
Yeah, so each tube is just a single sharp cutoff pentode.
Okay.
Pentode sounds confusing. There's 5 grids inside, hence the name penta. But really, we can ignore most of those. The suppressor grid is just to stop secondary emissions. The screen grid is to help with oscillations and help with when the tube gets close to saturation. The control grid is really the only one that we care about. So the suppressor grid's tied to ground, just like the cathode. Screen grid's tied to 24 volts through a small resistor. And then the control grid is what controls it. So we can really think of these as just fancy triodes.
Makes sense. So you just knocked this out one afternoon, right? It was a piece of cake, or is there a little bit of?
So we made a prototype. I machined the PCB myself, and I learned a lot on that. So I had cathode follower buffers on the op amps that I didn't need, and I doubled up on some tubes elsewhere. So it had 18 tubes, and that kind of parlayed into, oh, maybe I should make this correct, make it look like the real deal, order the PCBs so that they're not homemade. And I was like, I'll just transfer it over to there. So I ordered the first PCB, it showed up. It was so bad and so incorrect that I had to make a revision 2. And then I had to make a revision 3. And then I had to make a revision 4 because I kept making mistakes. And so now we're on revision 5 and finally it's good. I'm so proud of the fact that there's no bodge wires on the back.
It is a beautiful thing.
It took a huge amount of effort to get there.
Have you connected up and used it as an oscillator or some other application just to demonstrate it?
So it works fantastically as a demonstration tool. It is a terrible 555. It's like the worst 555 on the planet. It has speed limitations, so we run into slew rate problems very quickly. So where a normal 555, you can like spin it up to like 300 kilohertz before you start running into issues. This one starts to peter out at like 20 kilohertz. So not great, right? Not a great start there. And because we're at such low voltages, even with a cathode follower buffer on the output, the actual amount of current that we can push into our output is minuscule. I can get like maybe 10 milliamps.
So there's a reason that IBM didn't start selling 555s back in 1947 when these tubes were first available?
So that's actually an awesome question. Why did this design have to wait until the IC age? And that's because the 555 is great because it's so versatile, but you only really build it to do one job. And yes, you can use the 555 timer to do multiple jobs, but when it's in circuit, it's only doing a single job. And if you want to do just that single job, there's a better way to do it with vacuum tubes that's smaller. So the 555 as an IC worked out great because it was tiny. This is not tiny. So if I want an astable multivibrator, I can do that with 2 vacuum tubes. There's no reason to have this many in there. So back in the day when you were actually building genuine vacuum tube digital circuits, you would just build what you needed because it was going to be smaller, it was going to be more efficient, it was going to work better. But when they got to the IC age, the 555 is so tiny, it fits on the tip of your finger, that they could actually use it in a multitude of different places without having to worry about wasting space.
Well, that makes sense. This has 14 tubes on it. That seems
Does it? Yes.
quite high by the standards of 1940s, 1950s electronics.
It is. It's very high. Part of that is because I'm using the low voltage, so plus 24 and minus 12. If I was using, say, plus 100 and minus 100, I could get away with a single amplifier stage. That would eliminate 4 tubes right off the bat. But other than that, I mean, there's not a whole lot other optimization I could do other than changing to double triodes. So these are pentodes, which means there's essentially 1 element per glass. But a dual triode has 2 elements per glass. So I could take one of the op amps and cinch it right on down to just 2 tubes if I was using dual triodes. And then the SR flip-flop would come down to 1 tube if I was using dual triodes. And if I was really crazy, I could get into like compactrons, which are like triple triodes, or I could use double pentodes to achieve really weird stuff. So there's a lot of really esoteric and neat tubes out there, and you could probably get all of this down to like 2 or 3 tubes if you were really on it.
Next up, we've got a chat between 2 legends, Bill Hurd and Jerry Ellsworth. Now, as with all the other interviews we did, the original intent was to edit it down and put it on the YouTube channel. But before we even wrapped up the camera, Bill Hurd and I both felt that just so much ground was covered in this particular conversation that editing any of it out would have been, a shame. So what you're about to hear is their complete exchange, which does bounce around quite a bit from topic to topic, but, makes for an enjoyable ride.
So go ahead and introduce yourself.
I'm Jerry Ellsworth. I'm the co-founder and CEO of Tilt 5.
And what is Tilt 5?
Tilt 5 is an augmented reality gaming system. So you wear these glasses and holograms pop out of the table, sit around with your friends and play video games or board games.
You didn't just hook circuits together to make that. You found something one day in a lab.
Yeah, what was interesting is I was working at Valve Software, and I was trying to solve some of these other problems in AR, VR, where you try to put displays really close to your eyes. And I actually put a component in backwards, and I was projecting this light field out into the lab. And one of my co-founders had a piece of retroreflector on the wall. He was doing laser bounce experiments, and I saw this beautiful image like 30 feet away from me. And at first, I didn't think much of it. But many months went by, and I kept trying to solve these problems, and then just came to me one day at home, and it's like, well, maybe I should just turn the optics inside out and just emit the light field from the glasses, have it return directly back to each user. And so that was the key to make a really great AR experience.
So you designed the Commodore 1 in what year and what was it?
Oh my gosh, Commodore 1 was an FPGA reconfigurable computer in around 2000, if I recall, maybe 2001. Met you, Bill.
2010 maybe.
No,
Oh,
not 2010,
2001.
2001.
That's
Yeah.
right.
We were using Altera FPGAs, which were extremely small, but we managed to cram most of the Commodore 64 into these FPGAs, and we made this ATX motherboard that could be reconfigured through a compact flash card of all things.
So you were essentially the first person to emulate Commodore hardware, or was there others out there?
As far as I know, I was the first to do this. Yeah, and it wasn't easy back in those days. The tools kind of stunk, and the FPGAs were extremely small, so you had to do a lot of optimization just to try to get it to fit. And thanks to you, Bill, you helped me optimize a few things on the sprite circuit tree.
I had a guy tell me about, there's a bug in the sprite circuit in that, and he's telling me this, and I'm like, I did the sprite collision logic you're complaining about. I mean, he couldn't believe he's standing next to the guy. So you're well known for your early videos in the electronics industry. Tell us about that. What was your first, or what made you want to do videos?
So I got into making videos before I think YouTube was really much of a thing. So I was working in a company called New Tech that back in the day for the Amiga computer made the video toaster, which was the first kind of affordable video switcher. Later on, many years later, they hired me to work on a PC version called the TriCaster. And so the TriCaster's goal in life was just to make streaming out to the internet easy. And it wasn't easy around 2006 or so. So I was working on this project with them, and I had the prototypes there. And I'm like, maybe I should figure out what this video streaming thing is all about. So I went on Justin TV and Ustream, which were two services, and just started live streaming my hardware lab 24 hours a day, which everyone thought I was insane to do. And then I started collecting up like fans that would just tune in and watch, and they helped me modify the TriCaster so that we could have pan-tilt zoom cameras so they could zoom in on my workbench and see what I was working on, which was awkward sometimes working with other clients' technology. I'd have to like block it off so they couldn't see everything. But that was interesting. So I was doing the live streaming thing. I ran into George Sanger, who he goes by the Fat Man. He's a famous video game song composer, music composer. And he's like, you know electronics, I know nothing about electronics. Let's just do a show every Sunday where we just live stream and you invent something and then you explain it to me. I'm a dummy. And so we started doing that, and it picked up some traction. And we started gathering some folks around the Portland area where I was based. And we would start having these hack weekends where we'd start on Friday or Saturday, and we tried to do really difficult electronics or science or chemistry and get it all done by Sunday when we went live. So sometimes we succeeded, we got something done, and sometimes we didn't, but the show has to go on, so we just showed whatever we showed. About the same time YouTube was coming out, and didn't think much of it because it was really crummy quality and only 10 minutes, so I just randomly uploaded stuff. But YouTube took off and people started requesting more content on YouTube, so I kind of shifted my focus over there over time.
So what do you think of the crowd that we have here this weekend?
Oh yeah, so the crowd here at Vintage Computer Festival East is amazing. I came here 16 years ago. I think it was probably pretty early on in starting this event, and it was very intimate and small, maybe 1 or 2 rooms. Now it's like taken over this whole like facility, which this facility is amazing. There's a computer museum, there's trains, it's an old military base, I believe, and there's just all kinds of things to look at. But it seems like almost every room around here now has like some vintage computer thing going on in it, and it's really grown over the last 16 years. And what's amazing is I'm seeing so many women here and children, which is amazing. And they're having a great time, which really warms my heart to see that.
Excellent. So final question. What's your favorite online electronics-based magazine? Hackaday.
Oh, of course, Hackaday is my favorite place to go whenever I want to find out what people are doing. You know, Hackaday is amazing. Back in the day, when I was doing my early YouTube videos, Hackaday would amplify and promote various projects I was working on. So you always can go there and find something interesting every single day.
Well, I think that about wraps it up for this special episode of the Hackaday podcast. Thanks to the folks that took the time to talk to us at VCF, and thanks to you for listening and sticking with me this long. As always, if you want to see the show notes or leave a comment, you can head over to hackaday.com/podcast. If you see anything cool or do anything cool, send it in to tips@hackaday.com. And if you'd like to spend your evenings chatting with your favorite tech writers, you can join our official Discord server by pointing your browser to hackaday.com/discord. Until next time, keep on hacking. Somebody else is actually supposed to do that last part, but it's like 1 a.m. when I'm doing this, and who else am I going to ask, right?